Let's see, we don't need to go over that. I just want to reiterate, look, the polynomial function looks like this. And so let's talk about what you can't have. In other words, the exponents must be non-negative integers, we said. So which means you can't have variables in the denominator, because that means you really have a negative exponent. You can't have radicals, because it means your exponent's really a rational, or a fraction. You can't have that. You can't have absolute value, because you just can't. It has to look like this. Now, each term has its own degree. So this is degree 3 polynomial, degree 2 polynomial. The exponent is basically the degree. If there were more than one variable, it'd be more complicated than that, but there's not. So like I said, there's degree 3, degree 2, degree 1. The constant is considered a degree 0 term. Okay. The degree of the whole thing is the degree of the biggest degree of any of the terms, which we normally put out front. Okay. And so I just want to say again that leading term is what we use to figure out the long run behavior, because it dominates in the long run. To put things in perspective, let's say this is x to the power of 8. Then this term would be x to the power of 7, and so forth. This term would be, like, let's say x is a million. In the long run, you'll hit a million at some point. This term is a million times bigger than that term. You go even further, where x is a billion. Now this term is huge, and this one's also huge, but this one's a billion times bigger than that one. And then trillion is trillion times bigger, and it just gets bigger and bigger. And so once again, we use this as our long run model to know how it behaves in the long run. The book calls it the leading term test. I'm not used to using the terminology, but that's what they mean, is look at the leading term and figure out from that. So this example, that's a degree what polynomial? I keep asking the question when it's right there. I didn't. And then once again, this is the same exact polynomial, just in factor form. So here, you know it's degree 5 because you just look at the first term. Here, you need to figure it out, and just really, you have to imagine, once again, if you were to simplify this, the first term, you have to figure out the first term would be x to the power of 5, and just do your exponent rules. In this case, you're just adding exponents, and you get the 5 that way. All right, jump ahead. Now, your models, just want to remind you of this. Your two base models, if it's an even degree, it's going to look like a parabola in the long run. It doesn't mean it's going to connect like a parabola in the middle, just in the long run it'll act like a parabola. Where if it's odd, it looks like x squared. One thing I want you to note is that normal is to be up on the right. People always get this confused. In other words, look, if it has a negative coefficient, then those basic models are upside down, right? And now everyone always recognizes that, okay, that's just upside down even. But they're always getting these confused. They're not sure what's normal, because, it's going up on one side, down on one side in both cases. So I'm telling you, normal is to be up on the right. And so you can recognize an upside down odd, or anyone that's upside down, because it's down on the right. All right? So those are your long run models. One thing I would just want to mention, like, we're talking about polynomial functions, which this is, but it's a special case. So this is just x to the power of 4, shifted right 1 and vertical compression by factor 1/2. Yes? Listen, if I tossed in another factor like that, then you couldn't analyze it the same way. It's not just a parent function. And that's mainly what we're focused on now. 2-1, in other words, focused on power functions and transformations of power functions. The rest of it is dealing with polynomial functions that are not parent functions. All right? So you need to be aware of that difference. All right. Here. Well, actually, I'll get back to that. Here, we have this one. Find this example. We've already done it. I'm going to re-explain it. And if you want to hear it, you can write this down. So it actually lists all the zeros and their multiplicities. Basically, for the zeros, figure out when each factor is 0. Well, this one is 0 when you plug in 2, this one when you plug in -1, this one when you plug in 3. And then the multiplicity is just the exponent. So this one has an exponent of 1, so it's multiplicity 1. This one's multiplicity of 3. And 3 has a multiplicity of 4, so the exponent is 4. And once again, the multiplicity has two purposes. One is to keep track of how many zeros it has. By the way, I keep saying that word, but what is a zero of a function? What does that mean? A zero of a function is x value that what? Makes the y value 0, makes the function equal 0, yes. Okay? And so remember, that's what these are. They're x values that make the y value 0. And so if this degree, and actually, what is the degree of this polynomial? Yeah. If this is a degree 8 polynomial, it will have 8 zeros altogether. But when I say it has 8, that includes the multiplicity, and also includes imaginary zeros. Which this one does not have any imaginary zeros. I know that because I've already listed all the zeros and they're all real. And I know I have all 8 of them because this multiplicity adds up to 8. Okay, so that's one purpose of multiplicity, is to help you keep track of how many zeros you have. The other purpose, the main thing we're going to use it for now, is for graphing. And so, look, here's your 3 possibilities. If you have a factor with a multiplicity that's even, then when you go to graph it, it's like here. We had these factors with those exponents. We get these zeros with their multiplicities. Well, the even ones will look like this. They'll, around that part of the graph, around that x value, it'll behave like a parabola. Whereas if it's odd multiplicity, it's going to cross. And so it either touches or crosses. Even it touches, odd it crosses, but it can cross 2 different ways, linearly or with inflection. And it's going to be with inflection if it's odd, but it's more than 1, 3, 5, 7, anything like that, because it's going to look like x cubed, or x to the power 5, or x to the power 7, around that. Whereas here it's going to look like x to the power 1, or x, which is right, it crosses linearly. So that's the main point right now to multiplicity, is it tells you the behavior of the graph around that 0. Okay? Which is what that says. And we already did that one. I just want, here's the graph of this, and just note again, like at -2, -2 comes from this one, and it had an exponent of 1, which is how you would known it would cross linearly. 0 comes from this factor, which has an exponent of 3, which is how you would have known it's going to cross with inflection. And then 3 comes from this factor, which has an even exponent, which is how you know it would just touch there. Okay? All right. How about turning points now? Look, it's easy. A turning point is simply where it turns from increasing down to decreasing, or from decreasing to increasing. In other words, you're dealing with either a local maximum or local minimum. And these, once again, they're called, like that's, you can call it a local maximum because it's the maximum y value in that area. It's also known as a relative maximum because the maximum relative to these points, but it's not the maximum y value overall. This one doesn't have an absolute maximum because it goes on to infinity, right? So, like I said, if I use this term turning point, I'm talking about the extreme of the graph, the local maximum or local minimum. You're not talking about inflection points. Look at this right here. The graph is decreasing, and then it's decreasing again, right? So it didn't turn from increasing to decreasing like it does here, or turn from decreasing to increasing like it does here. In calculus, by the way, you find that the derivative here is 0, the derivative here is 0. At every one of these points, the derivative is 0. But this one, once again, is not a turning point. So just be careful about that. All right, so look at this. You have this in your paper. I want to do the zeros all the way across first. Before we start, if you look at these 3 graphs here, are they even or odd graphs? Even because they all start high and end high. And they're also normal, the positive coefficient, because they start high and end high. These are all odd, and they're normal. And they're odd because they start low and end high, and they're normal because on the right they're high. By the way, this is even because they're degree 4. It kind of tells you. These are odd because they're degree 3 for the shape. All right, let's do the zeros first. So the blue graph has how many zeros? Just 1, yes? Write that down. The red graph has 2 zeros, and the green graph has how many zeros? None, yes. Let's do the odd ones. The blue one has 1 0, the red one has 1 0, and the green one has 2. Now, the point of this is to figure out what's the max and min you could possibly have. Well, right here, if it's even, it could have none. So the minimum you could have is 0 in this case. None of these have none, but is it possible for an odd function to have no zeros? No, because if it starts at negative infinity for a y value and ends at positive infinity for a y value, it's going to hit 0 for a y value somewhere along the way, isn't it? So the minimum here is 1. And so these two have the minimum. This one had more than minimum. Let's talk about the maximum now. None of these actually has the maximum they could have. Watch this. Like here, if the if the x-axis had gone through that part of the green graph, just focus on the green graph now. It could have had 3 x-intercepts, couldn't it? Right? And so I want you to just note the maximum here would have been 3. Over here, watch, just focus on the green graph again. If I had the x-axis go right through there, how many x-intercepts would that be? Right? If it went through here, It could have 3. If it went through here, that'd be 2, or up here would have been 2. It could have 1. It could have none. What's the most it could have had? 4. Here, I want you to write this down real quick under that table you have on your paper. So if you're talking about zeros, the minimum is 0 and 1, but the max is just always n. We'll get back to that. No, just focus on zeros for now. We'll get back to that. Let's do turning points now. All right, over here, the blue graph has 1 turning point. Right, that minimum is a turning point. The red graph has how many turning points? Also 1, because that inflection point doesn't count. Once again, it's decreasing, then it turns and starts increasing. Then at the inflection point, it continues increasing. So, like 1 turning point. The green graph has, good. Over here, the blue graph has how many turning points? 0. Once again, the turning point is either maximum or minimum, and that blue graph has none. The red graph has 2 turning points, and the green graph also has 2 turning points. Now here, you can see the minimum. I mean, you could have none, apparently, because it had none there. Could an even graph have none? No. Because if it starts high and ends high, it must have turned at some point from decreasing to increasing. So here, the minimum is different. And these are related, obviously. In other words, because this thing must have 1 turning point where it turns from decreasing to increasing, then it could happen that it has no x-intercepts, right? And over here, the fact that it could have no turning points means it must have 1 x-intercept minimum. So, now, as far as the maximum, none of these have the maximum. No, I'm sorry, I said that wrong. I was getting myself confused. They both have the maximum in these examples. The most you can have is always n minus 1. So on the table, here, fill the table. So like the maximum number of turning points is always n minus 1. And listen, that could be a test question. You're given an equation that says, okay, how many turning points could it have? And it could just list multiple choice, which of these is a possible number of turning points. It could ask what the minimum is, what the maximum is. My point is, if you don't remember this rule, I don't want you just memorizing things. Figure it out. If nothing else, do a few typical examples. You should know what a typical odd or typical even looks like, and figure this out. All right. This is not in your paper. Only find a place to write this down. Just write the equation down, and it's going to take a little bit of work, a fair amount of work. So either get a blank sheet of paper or put it somewhere on your paper. I want you to understand the notes I'm using are the ones I've been using, and so our new book, it covers the same material. The questions are phrased slightly differently. For instance, it says using the leading term test. I don't call it that. We've been doing that. When you look at the first term and you decide whether it's an even or odd, that's a leading term test. Here, we've done this kind of thing. It's just really the factoring that I want to focus on here. Okay, we've done this kind of factoring before, but it bears repeating. So it says first we'll state the number of possible real zeros. Here, I'll put it this way: max number of real zeros. I can write the word real. That would be 4, yes? It is a degree 4 polynomial, so we have 4 zeros. What about turning points? Maximum number of turning points. Yeah, because it's always n minus 1. And once again, let me say, since it's a degree 4 polynomial, it will have 4 zeros. They could all be imaginary, though. Okay? So when it says number of possible real zeros, they could all be real. So it could have 4 distinct real zeros. Of course, it could have all real zeros, but they could all be repeated roots. In other words, you could have something like this, where it hits the x-axis at 5, and it has 1 real zero, 5, that counts 4 times. So I'm just saying, it could have, it will have 4 zeros. It could have at most 4 real zeros. Anyway, let's back to this thing. So first of all, well, here, we're going to do the substitution. In other words, if I call x squared u, then my equation becomes like here. The 13x squared becomes 13u, and x power 4 becomes u squared. And then that just once again makes factoring easier. You want numbers that multiply by 36, that'd be 4 and 9, and they add up to 13, so there's your factors. And when does this equal 0? When u is 4, here when u is 9. Of course, we don't care about u. We want to put x squared back in there. And x squared does not equal 4 when x is 2. It equals 4 when x is 2 or negative 2. Here the answer is not 3, it's 3 or negative 3. And technically we're done. It just said determine all the real zeros, and we did that. Okay? I do want to take this a step further, though. Now, we have 4 distinct zeros, so if I wanted to list the zeros with their multiplicity, and you don't have to make a table to do this, but this works. You have, like I said, 4 distinct zeros, each with the multiplicity of 1. All right? And this is a degree 4 polynomial, so that's the whole list, right? And let me go a step further. If I wanted to write the equation in factor form, then the original equation was like this. Now I can say, well, it's x squared minus 4 and x squared minus 9. Or in other words, it's x plus 2 times x minus 2 times x plus 3 times x minus 3. So once again, you had 4 distinct zeros, so you have 4 distinct factors, right? Now, the point with going through all this is contrast that case with this case. Let's say instead of that equation, I give you this equation. And so there's that, and there's this. Not the same thing at all. Now if I ask you to list the zeros with the multiplicity, you have 2 distinct roots, positive 2 and negative 3, each with a multiplicity of 2. Yes? And people confuse these two situations. And so I'll give them this case up here, and and then if I give them to them this way, they'll say, oh, it's 4 with a multiplicity of 2, or 2 with a multiplicity of 2, and 3 with a multiplicity of 2. And no, it's not. So I'm just saying, be careful with this. This is not what we're doing right now, so don't confuse them. All right? All right, let's move on. We're not going to do that one. All right, you have this. Are you looking at an even or odd graph? Tim? Even or odd? What are you looking at? It starts low and ends high. So is it odd or even? It is odd, in fact. Even is the ones that look like a parabola. And when I say in the long run, if it starts high and ends high, that's even. If it's opposite directions, then it's odd. Okay? Is this normal? In other words, is the coefficient positive or is it negative? Positive, because on the right it's going up. Okay? So I would immediately make sure you know whether the coefficients are positive or negative. And if it's negative, write the negative sign down now before you even get started, because people always forget the negative sign. Now, as for the roots, well, that's easy. And 2. And then their multiplicities are easy. Here, since it touches, it just bounces off. You know it's even multiplicity. So multiplicity of 2. And technically, it could be 2, 4, 6, 8. We'll go with the smallest possible, so 2. And then here, it crosses linearly, so that has a multiplicity of 1. And listen, as far as listing the roots, if you want to put x equals negative 3, x equals 2, you can. You can just put the numbers. They are x values, of course. Now you're supposed to write the equation. So if negative 3 is a root, plus 3 is a factor, and 2 gives you x minus 2 as a factor, and x plus 3 is supposed to have an exponent of 2 because its multiplicity was 2, but x minus 2 is 1, which I won't write. Now, we need to get the coefficient right. We know it's positive, but need to figure out what it's actually supposed to be. I would write the y-intercept down. It's given in the graph. It's just 0, negative 18. But that's what you're going to use to figure this out. So listen, if you plug in 0, then our function, our answer, better produce negative 18. And if it doesn't, then we need to figure out what coefficient to put here to make it work out to negative 18. If you plug in 0 here, you get 3 squared is 9. If you plug in 0 here, you get negative 2, which is negative 18, which means we're done. The coefficient is 1, we don't have to change it. But that's how you figure it out. Okay? How many turning points are there? 2. We're supposed to list them here, though. So, and I want you to categorize them. So there's one max, one min. The max is at negative 3 comma 0, and the min is, well, at this point, gave it to you. And listen, they won't always give you the turning points, but if they don't, then they can't ask questions like the intervals of increase and decrease, right? By the way, just to get the right perspective here again, hold on. Look, it's increasing, increasing, increasing. The y values hit a maximum of 0 here, right? And then they start decreasing again. So here, it was increasing until it got to negative 3. Then at negative 3, it turned downwards. And so now from negative 3, it's decreasing until it gets to when? Zoe? When does it stop decreasing? Because that's the next turning point. It turns upwards there and stops decreasing and starts increasing. And so now it's increasing from 0.32 on forever. So once again, the turning points are the breakout points from when it was increasing to decreasing, and vice versa. I don't know. I don't remember what the actual test looks like. I didn't look at it last week. So as far as the exact format of the question, I don't recall. In other words, will it have blanks? I don't know. If it doesn't have blanks, then just list them, write down like this. If it has blanks, then use the blanks. We'll see. All right, the other example is going to go a little quicker. Any questions about this one? All right, then let's do this one. Is it odd or even? Odd again, but now negative coefficient because it's down on the right. So once again, I would immediately write down it's y equals negative whatever. So you can't forget. The roots are what? And 1. The first one has a multiplicity of, we'll say 3. And for multiplicity, you can shorthand it like that. Look, the multiplicity tells you the behavior of the graph around that 0. And because it crosses, it's odd. Because it crosses with inflection, it's not just 1. It could be 3, 5, 7. We'll go with the smallest possible. Yeah. And so over here, it touches, so it behaves like a parabola. So we know the multiplicity is even. 2, 4, 6, 8. We'll assume 2. Okay? So by the way, that means our answer is going to be a degree 5 polynomial, because the exponent's out of the 5, right? And once again, if negative 4 is a 0, x plus 4 is a factor. And the 1 here gives you x minus 1. The exponents are 3 and 2. Y-intercept, you need a note. We're going to write it down. Now, if you plug 0 into what we have so far, plug 0 here, you get 4 cubed is 64. Plug in 0 here, you get negative 1 squared is actually 1. Well, at this point, you would have realized that you need a negative coefficient if you didn't already have it, right? But it means we're done. The coefficient is actually just negative 1, because it already works out to the correct y-intercept. If it had worked out to, let's say when we did the math, or actually let's say the y-intercept was negative 128. Well, that means you need a coefficient of negative 2, right? Because when you plugged in 0, you didn't get 128, you got 64. So that's how you figure it out if it needs to be something other than 1. All right, turning points. How many are there? 2. Yeah, this one does not count. So it has, like this one's the local minimum. Can't write today. and then the maximum is at 1 comma 0. And then Aisha, it starts out decreasing, yes? So it's decreasing from negative infinity till when? Good. Once again, at negative 4, it was decreasing before negative 4, it's still decreasing after, so that was not a turning point. It turns from decreasing to increasing right there. So then it's increasing from negative 1 till 1, because that's here. And from then on, it's decreasing again. From 1 to infinity, it's decreasing. So once again, what are the turning points? The points that separate from when it's increasing to when it's decreasing, and vice versa. All right, you try the next one. I will say it's even. It's a normal even, right? But now you try. Any questions about what I have so far? The y-intercept, of course, is negative 54. And this one's boring because if you plug in 0 here, you get 3 cubed, which is 27. Plug in 0 here, you get negative 2. And so it works out to negative 54, which is what area is. So once again, if the y-intercept was like negative 108, then you'd know you need to put a coefficient 2 in there to make it work out to the actual y-intercept. Now, there's only one turning point, which means there's only 2 intervals that we need to write down. This thing starts out decreasing, and so Caleb, when does it stop decreasing? And then it's increasing hereafter, forever after. All right. All right, one more thing. This is a little different. You already have this. So first of all, what's the degree? 4. And yes, thank you. And the long-run model is just that first term, so y equals x to the power 4 is a long-run model, which means in the long run we expect this to go up in both directions, right? Part B, find the x-intercepts. For this, we're going to have to factor this thing here. So, first of all, x squared is the common factor, so factor that out. And then the factoring there is easy. You get x minus 4 and x plus 2 as the factors. So, the zeros, you get x equals 0, x equals 4, and x equals negative 2. These are zeros of the function. And then, it doesn't say to write the multiplicity, but I think it's a good idea. It's not behaving. Okay, so here, with this exponent, it's an exponent 2, so multiplicity of 2. These both have exponent of 1, so they're both multiplicity of 1. And that means here it touches, because it's even multiplicity, whereas here it crosses, because it's odd. And I'm going to go a step further and say it crosses linearly, which is just 1. It doesn't cross any inflection. Now, once again, we put everything together. We're supposed to draw the graph. In this case, it tells us the turning points. And listen, if it doesn't tell you the turning points, then most of the time you can't figure them out. And then it can't ask these questions about like intervals of increasing and decreasing because you won't know exactly where the turning points are. And sometimes it will and sometimes it won't, right? So anyway, here, let's start creating our sketch. Where were the zeros? Oh, here they are. 0. Don't forget to put an x-intercept at the origin in this case. And then negative 2. And positive 4. And then the turning points, there's 1 at negative 1.4 comma, what was it, negative 6 point, okay. Just estimate it, somewhere in there. And the other one is at 2.9 comma negative 45.3. This is not exactly the scale. My x-axis and y-axis are definitely not scaled the same. It's okay. Now, other thing is, okay, what do you want to have in your graph? Your intercepts. Where have our x and y intercepts? Actually, I forgot about that. The y-intercept is actually still, it's the origin, of course. And since one of the x-intercepts is the origin, that's also the y-intercept. But you're supposed to have written that down. I'm just saying, make sure you have your intercepts on the graph. Your long-run behavior, we said since it's even, it's going to start high and end high. And I would write that like off to the side, and as a guide. And then you just go through your zeros. So start above this one. And be careful. In other words, look, at -2, it's supposed to cross linearly to do so. It's going to bottom out there. It's in the minimum y value of -6.4, then turns upwards. And then at 0, it's supposed to just touch, and then come back down. Then it comes down, hits that minimum, turns back upwards. And then at 4, it's supposed to cross again. Actually, I think when it gives you the turning points, it makes it easier, because you know you're going to have to hit these points. Usually, frankly, they don't give you the turning points, and so you have to realize, oh, it's going to hit some minimum. You just won't know where the minimum is. And then you have to know it's going to hit some minimum here. You just don't know where it is. I think it's easier to mess up though if they don't give you the turning points. Now, we need to do the rest of this. Any questions about the graph? Then here, the domain is easy. It's all real numbers. And it's always going to be all real numbers for polynomials. The range, we can only do because they gave us the turning points. The minimum y value is right here, yes? Now this thing has 3 turning points, which means it has 4 intervals of increase and decrease. It starts out decreasing. When does it stop decreasing? Hayden? No. It is increasing from -1.4 to when? 0. X value 0. And then from x equals 0 to x equals 2.9, it's decreasing. And then it turns upward, and then from then on it's increasing. So 2.9 to infinity is increasing. And you're done.